Hi, I'm Aaron Roth, and I want to talk to you about some work that I've done with colleagues here at Penn, Alex and Scott, about resolving predictive multiplicity and thinking about individual probabilities. So in the practice of machine learning and statistics, we very frequently predict individual probabilities. What do I mean by this? Well, things like the probability that it will rain tomorrow in weather forecasting, or the probability that Alice will die in the next 12 months in life insurance, or the probability that Bob will be arrested for a violent crime 18 months after his release on parole, or the probability that Carol will develop breast cancer before the age of 50. Things like this. These are events that occur only once, and so we don't have the luxury of observing repeated trials and measuring these things. Right? Tomorrow happens only once. Alice has but one life to live, and so on. And so it's very difficult to try to claim that we get these probabilities exactly right because we can't measure them. And if you sort of think hard about it, you might even wonder whether these things are properly grounded in the real world. So this is something that philosophers of science worry about. It's also something that has come up in the fact literature under the name model multiplicity or predictive multiplicity. And I want to briefly give you sort of the perspective of both fields on this problem. So in the philosophy of science, this is very closely related to what is called the reference class problem. And to give you the classic introduction to the reference class problem, let me describe to you the case of United States versus Shinobi that has become sort of a traditional example in this area. So Charles Shinobi was a 34-year-old Nigerian citizen living in New Jersey, working as a toll booth operator. And he was caught at the airport at JFK with 103 balloons filled with heroin. And he was arrested and he was convicted. And although he hadn't been caught, from passport records, it was believed that he'd made 8 other drug smuggling trips. And the sentencing guidelines in this case required that the court estimate the total quantity of heroin smuggled across all of his trips, not just the trip he was caught on. Okay, but since he hadn't been caught for the 8 other trips, this hadn't been measured. And so what do you do? Well, a government statistician was tasked with producing an estimate, and he did what is perhaps a reasonable thing. He said, okay, well, what is relevant about Charles Shinobi? Well, he's a Nigerian drug smuggler apprehended at JFK between, some particular dates. These were the dates of his first and last trips. And so he said, okay, well, we've within these dates arrested other Nigerian drug smugglers at JFK. We know how much we know how much heroin they were smuggling. And so we'll just assume that Charles Shinobi was smuggling the average amount among all of the people in this reference class. Okay, so here, Nigerian drug smugglers apprehended at JFK is some reference class, but is it the right one? Why is it relevant that he was apprehended at JFK? Why is it relevant that he was Nigerian? There are other reference classes he was a member of, right? We could have compared him to drug smugglers of any nationality apprehended anywhere. We could have conditioned on other things. We could have looked at drug smugglers living in New Jersey apprehended at JFK. We could have looked at people who work as toll booth operators. These are all reference classes that Charles Shinobi is a member of. And yet, if we had computed this average by averaging over these other reference classes, we would have gotten different answers. Okay, so since Charles Shinobi is a member of all of these reference classes, what privileges one of these answers over another? This is the reference class problem. Okay, very closely related is the model multiplicity problem or the predictive multiplicity problem that people in the fact and adjacent literature study. Right, so when we train a probabilistic model to predict things like the chance of recidivism or the chance of dying within the next 12 months, we are implicitly committing to a model of individual probabilities. But since individual probabilities are unobserved, we can only sort of measure things over reference classes. How do we adjudicate between 2 different models? If we've got 2 different models that make different predictions, which is the right one? Now, one way of doing this is to measure accuracy, right? Over a large collection of people, we can measure the accuracy of these models in aggregate, and this has good foundations behind it. The true individual probabilities will in fact minimize squared error. So if you have 2 models and one is more accurate than the other, the less accurate model has been falsified. It cannot represent the true probabilities. But it can be that I've got 2 models that are equally accurate, neither one falsifies the other, and yet they make very different predictions on lots of people. This is sort of the model multiplicity problem or the predictive multiplicity problem. And again, we can ask, what should privilege one of the models over another? Okay. So our contention, and our paper is mathematical, we formalize all of this with theorems. Our contention is that although individual probabilities are in fact fundamentally unknowable, you can't solve that problem. Two analysts who agree on the data, or at least on what the data distribution is, on how to sample new data, cannot in good faith agree to disagree very much on many individual probabilities. Okay, so in some sense, the punchline is something like the model multiplicity problem can't actually arise at scale in good faith. Okay, so here's the basic idea. And again, we formalize this all algorithmically and mathematically in the paper, but the idea is simple. Suppose you've got two models, F1 and F2, and they've got large disagreements on many people. There's a lot of people that these two models predict very different probabilities for. Well, let's look at their disagreement regions. There's the region A, on which it's the set of all people for which model 1 predicts a higher probability than model 2. And we've got region B, the set of all people for whom model 2 predicts a higher probability than model 1. Okay, since the two models disagree on many people, at least one of these regions has to contain a lot of people. It has to be big. But say it's model A, right? In region A, model 1 systematically predicts higher probabilities for the outcome than model 2. And since A is big, we can measure the propensity of the actual outcomes. So one of these models has to be wrong on region A in a way that we can measure and falsify from reasonable amounts of data, because A is big. That is to say, one of the models must have large statistical bias on one of these two large regions. And if we discover a region in which a model has large statistical bias, we can fix it. And in fixing it, we've improved the error of the model. We've decreased the error. We've made the model more accurate. Now, everyone should agree that this fix is good, because not only have we made the model more accurate, we have sort of eliminated a region of the model in which its predictions had previously been falsified. Now, maybe our two new models agree almost everywhere, and we've resolved the predictive multiplicity problem. Or maybe they don't, in which case we can repeat this procedure. But because every step of this procedure decreases the error significantly, and the error can't go below 0, this process can't go on forever. It has to quickly halt at two models that we both agree are better than the original models, but that themselves agree almost everywhere. So the theorem that we get for our very simple algorithm is that there's a reconciliation procedure, a simple algorithm, such that if you feed into it any two models, then within a reasonable number of rounds, it'll spit out two new models that, number one, everyone agrees are better than the original models in that they are more accurate, they have lower error, and the models that are spit out are not empirically falsified on the reference classes S that we have identified over the course of the algorithm that have empirically falsified the original models. And these two new models agree on almost all of the individual probabilities they predict. That is, the model multiplicity problem has become very small. Okay, so everything here is efficient and constructive. We've got modest computational requirements, modest data requirements, and all of this is to say the quantitative degree of disagreement can be quickly driven to 0 with more data. Okay, so what's the upshot? Well, participants can have sort of maybe more fundamental disagreements, like what the data distribution even is, or what the data really are. But if participants agree on what the data is or how to sample from it, then severe versions of the predictive multiplicity problem cannot arise in good faith, because if you and I have competing models that make very different predictions, we can reconcile them, get models that we both agree are better, and agree almost everywhere. And you might ask, well, hasn't the predictive multiplicity problem been observed empirically? The answer is yes, if what you do is the traditional thing in machine learning, which is to find a model by minimizing error in some fixed class, then the model multiplicity problem can arise. The trick is that the reconciliation procedure we introduce cross-calibrates these two models and results in new models that are outside of the original class. That's important. And so, although individual probabilities are, in principle, unknowable, we can't solve that problem. What we show is that they are contestable. If you don't agree with the predictions made by my model, then you can propose your own model. And we can negotiate through this reconciliation procedure to agree on new models that are only improved and yet agree almost everywhere. Okay, so maybe like a punchline, we cannot agree to disagree about individual probabilities. Thanks. If you want to check out the paper, it's on arXiv. And if you want to know more about this sort of style of thinking, I taught a class on it, and there are notes and lectures available at uncertaintyclass.com.